This is chapter 3, and it's about the relational model and the process of normalization. So, what is the point of this chapter? I know you're all thinking that, having read it. What's the point? And here's the point of this chapter in my words. This chapter is about teaching us how we can design databases that are more pleasant to work with. Some database designs are easy to process, and others are problematic, like, in a nice word. And normalization gives a set of principles that improve the structure of a database so that some anomalies and annoyances in the way that things are processed are just completely avoided, and they can never happen. So this is sort of the right way of making a database. We may see later that sometimes we don't want all of these rules applying to us, and we may break some of these rules for performance reasons, but for now, we're going to add some to make things better. This chapter has a lot of terms that they want you to know before you can do anything. So we're going to learn some terms, and then we'll try to do some stuff. We're going to talk about relations in great detail, functional dependencies, which are kind of the source of a lot of the problems that we're going to try to solve. Determinants are connected to functional dependencies, and then talk all about keys, talk about the referential integrity constraint, and then talk about some normal forms. So first of all, what is a relation? When we think about a relation, we're generally thinking about a table, something that has rows and columns, but there are a couple more characteristics that have to be in place for it to actually count as a legal relation in the formal sense. So a relation is a 2D table that has the following characteristics in this list that I've tried to distill down. All the rows are representing entities. The columns contain attributes. Thirdly, all the entries in a column are about the same kind of thing. They kind of contain the same data, right? So there's all phone number data. It's all name data, yeah, in one column. The columns need to have a unique name. So there's a unique, non-duplicative, duplicated name for each column. Next, the cells need to hold a single value, not lots of different values. The column order is not important, so you can move columns around and it doesn't really change the consistency, the state of the database. And likewise, the row order is not important. You can rearrange those. And lastly, no identical rows are allowed. No two rows are the same. So if your data is in a 2D table and it meets these criteria, then you have a relation. Good? All right, so the book then goes through several examples of examples, positive and negative. Yes, sir. All right, so let's play a little game. Is it a relation? So we look at this data and tell me, does this set of data break any of those rules that we just talked about? And if so, what rule does it break? What do you see? What do you think? So Jason says he sees several phone numbers in one cell. So that breaks the only one item per cell rule. You are correct. You ready for this? Boom. No. Get out of here. Did you like that? You didn't see that coming? Did you really not see it coming? Because you know I love the anvil animation. I know I overuse it, but it's just, if you could do something that would bring you 1 ounce of joy and you were in control, wouldn't you do it more often? I mean, even if it was goofy? Yeah. Okay. Next. Is it a relation? Somebody besides Jason, what do you think? Seeing some no nods. What's the problem? The fax and home rows contain a different kind of data than email. Another way of looking at this is if the rows were moved around, we would lose that structure, right? We might understand that the facts in home under number 400 go with number 400, right? So either way you look at it, that's breaking a rule. So no relation. Get out of here. How about this? Are you sure? It's good. I just wanted to throw y'all off. It's that's a relation. That follows all of our rules. And lastly, this one, we've added a comment field which can hold different amounts of text, even lots of text. So what do you think? Does that still qualify as a relation? Everybody says yes? That's right. Good work, guys. I'm proud of you. All right. The author presents some alternative terms for relation, which relation is the same thing as a table, an attribute is the same thing as a column, and a tuple is the same thing as a row. Just different terms for it that maybe those more mathematically inclined might call it this. Also, file, field, and record are synonyms that could also be used. So if we use those interchangeably, no one freak out. All right, so next we need to talk about functional dependency. A functional dependency happens when the value of one attribute determines the value of a second attribute, or the value of a set of attributes determines the values of another set of attributes, or any combination of those. So something determines something else. And let's try to look at an example of this. The relationship we're talking about here, something determining something else, is based on the nature of the physical system that we're modeling in the database. All right, so in this example, we've got students, their IDs, their names, their dorm name, their dorm room, and it's the dorm fee. That's how we're going to look at it. So what dependencies exist within this data? Another way I like to think about it is, if I know the value of this thing, what other values will I know? Assuming this is laid out in the normal way. So I'm assuming that you have some knowledge here, which I think you do because you've worked in these kind of systems before. They sure do have the same first four letters, don't they? It makes you feel like they should do something. Let's assume that dorm room just has 205. You really sort of do have to look at the data or be able to talk to a person who knows the system, like the person who's in charge of the housing for the university would know the rules. Right? If we know the student ID, then we can figure out what the student name is. So the way to read this arrow is determines. So student ID determines student name. Make sense? What else might we know? Okay, so maybe the dorm name determines the fee. I like that. Right. Student ID should be unique for students. And if we know the student ID, then we know what dorm they're in, we know what dorm room they're in, and we know what the fee they paid is. So this is a way to list this out, each of these dependencies, each of these functional dependencies between student ID and these other fields. We can group them all together to say this more concisely in this line, putting them all in one line to say that student ID determines student name, dorm room, and fee. And lastly, somebody said this, I think we're going to say that the dorm name determines the dorm fee, So different dorms have different fees. So as we continue, sometimes you may understand that there are equations at play in the system that we're looking at. Like if we're computing an extended price, if we're recording an extended price in our rows, like for orders, that's the quantity times the unit price, then we could represent that equation, or the results of that equation are a functional dependency. Functional dependencies are not equations, but if there's an equation to compute something, then there is a dependency there. So quantity and unit price together determine extended price. We can't get extended price with either one of them alone, but together we can absolutely, definitely determine it. Does that make sense? So you can put the groups on either side. That is, you can have a composite determinant if the grouping is over here. But that means you need to know both things in order to know the thing on the other side, the thing or things. So this is functional dependency, and we need to know what this is because this is going to have a big impact on better ways of structuring databases. So if we have A determining B comma C, then what can we say about the relationships within those? Oh, somebody read. This makes sense. Really, it's just saying, right, putting B and C in commas is basically saying and. What if we look at it the opposite way? If A comma B determines C, then what can we say about these single pieces? That's correct. Neither A nor B alone determines C. Right? We have to have them together to have that dependency, to make that determination. Okay, so this is functional dependency. One way that we could analyze this is by looking at the data. And this can give us some insight into the dependencies that exist. So this is going back to our Cape Cod example. This is looking at the SKU data table. If we look at this, we want to ask what functional dependencies may exist within this data that we see. So if we know the value of one column, can we determine the value of another column or groups of columns? So what functional dependencies do you see in this data? And how did you see it? I guess would be the follow-up question I would ask. So you think that the SKU should determine the description? I agree. The SKU should determine the department, and the SKU should determine the buyer. Are there other relationships? Now, to be fair, we're not talking about primary keys yet. So in some sense, that's an additional tool that will come to bear later and to solve this problem. So, but if we just keep it to functional dependencies, which I know is hard, the keys are what we're going to do to solve this. This is what the book says. And some of this may be a property of the system. And I hear what you're saying, Alan. It seems right to me, too, that you could have different buyers for the same item, but apparently not in this system. Note this related relationship, that the SKU description is also unique for every SKU. So you could see that the SKU description determines the SKU, the department, and the buyer. Does that bother you? Yeah, so if you knew the SKU description, you could determine what the other ones are. Boom. Yeah, you did. So there is also this last relationship between buyer and department that, with this example, if you know the buyer, you know what department they bought for. That does seem like an artificial limitation to me of a real system, but I clearly don't understand all the intricacies of this business model. They go through and do the same thing for this order item table, where we have a different order number for every order. We have the SKU, the quantity, the price that was ordered, and then the extended price. So if we look at this, what functional dependencies exist within this data? Notice that order number 1000 has one of these things and one of these 202s. But both of those are order number 1000. You see that? So that's how we would accumulate multiple items on one order. Is it? So if you know the SKU, you know the price and the quantity?
Well, I guess you know the quantity from it.
Yeah, see, this guy ordered the same thing as this guy in order number 3000 and in order number 2000. So skew alone is not enough to determine everything else. Right. Order number and skew together will let you determine each of the other fields. So where Jason wants to go with this is, right, that means that if we put those together, we could see them as like a primary key, and we could uniquely identify every row based on that. There's one more in here based on the equation, which is if we have the quantity and price, that determines the extended price. Y'all good with that? Okay, so what makes a determinant a determinant? A determinant is unique in a relation if and only if it determines every other column in the relation. So one thing that we did to determine the determinant, to figure it out, was to kind of look and see, if I know this, can I determine what all the other columns are? And that's easy to do. It's easier to do, right, if there's just 6 rows, because then you might begin to say, well, yeah, well, this is unique. But it may be that that's not a true relationship in the system. It's just we have such a small set of data, we don't know that the real relationships that exist. It could be a limitation of the data set that you have. So to find determinants, we have to find determinants that are logically, that are actually the determinant. And you may need to talk to the real users of the system to know what really determines other things. Like, for example, does the dorm room affect the fee? That is, if your dorm is Sewell versus Faro, does that change the fee? I think it wouldn't at our university. I think it's the same housing fee regardless. So in that case, it's not a determinant, but it might be somewhere else. Okay. Now let's talk about keys. The idea of a key is just to uniquely identify rows in a relation. So a key is a combination of one or more columns that will uniquely identify a row. And there are so many keys, so many. It's important that you know what all these keys are, because in this class and in the real world, people will throw these terms around and you need to know what they're talking about. Many of these we've already seen. First of all, a candidate key. A candidate key is a column that determines all the other columns in a relation. So it's something that could be a key because it uniquely identifies every row. The difference between a candidate key and the primary key is the primary key is the one of the candidate keys that you've chosen to use as the unique ID. In that example before, remember that skew and skew description uniquely determined all the other columns, I believe. So either one of those, both of those are candidate keys, but we would almost certainly choose skew as our primary key because it's an integer and it would be much easier to deal with. It would be faster for the database to use. So there's only one primary key per relation. That key could be composite, and composite just means it's going to take into account multiple columns. We're going to kind of look at the key as the combination, almost the concatenation of 2 columns. But together, those would define the primary key. Ideally, the primary key should be short, it should be numeric, and it should never change. So that way we can always find and always look up, we can find, we can search, we can query the database using that unchanging short numeric key. Because of those properties, it is sometimes advantageous to add an integer ID to a set of data, even though that integer ID is completely arbitrary and isn't really inherently a value in the data set. And that's called a surrogate key. So this is a database supplied value. It is short and numeric and it never changes. It has artificial values that are meaningless to the users, but we generally won't show it to them. So it's just really a structure that we use to structure the database and make the database operate better. here's an example. If we have this table rentals, then we have to have the street, city, state, and zip to be our primary key to uniquely identify the rows in this relation. And so you see the only thing that's not in the key is the rate for that property. So in this case, that's a lot of information that we'd have to search when we're trying to do unique ID lookups in our database. It would be common, and this is what we've already been doing in our databases in the assignments, to add a property ID surrogate key so that there is this easy unique ID. So now the property ID is another candidate key, and we would choose that as our primary key. That makes sense? The foreign key is the last key we're going to talk about. I know, what a relief. And we've seen this before. Foreign key just means that we are connecting two tables together. So in this case, in the employee table, the employee relation, we have an employee number as our primary key. We have department name, which links this to the department that's listed up here in the department table based on name. And likewise, there's actually another relationship here. The manager number for this department is a foreign key to a certain employee in the employee table. And the way I've written this, according to the book's conventions, the primary keys are underlined and foreign keys are italicized. Does this make sense? Any questions on this? So a foreign key is a value that would be a primary key in a different table. It's foreign in the table that it's in, not primary. Does that make sense? Because it's out of its element. Y'all good? Are you really good? You're not talking very much. Let's throw out some more words. Referential integrity. That's fun to say. The referential integrity constraint is a statement that just limits the values of a foreign key to those that already exist in the primary key column of the corresponding relation. This should make sense, right? So if your department name is computer science, there has to be a computer science that's the department name in the primary key of the department table, if that's what's in the employee. So that makes sense. If you're making this link between two tables, if you start putting in values that don't exist as the foreign key, then your database is inconsistent, and that's what we don't want. We want to keep the database consistent. So the foreign keys must exist is the long and short of it. And our databases, like MySQL, when we define foreign key relationships between tables, they make sure that that constraint is actually followed. So you could never add a row that has a value as a foreign key that's not in the other table. Does that make sense? I feel like I'm not saying it super well. Yes. Which would be annoying, but it makes sure your database is consistent. So even if it's just numbers, if you say 8, if there's not an 8 in the other table, then it won't even let you put the row in. Okay, so this concludes our talk about keys. And now we have to talk about normal forms. Anyway, I love pizza, but you know their phrase, better ingredients, better pizza. For us, we're thinking better design, better database usage. So if we design it better, we make it out of better stuff. In our case, it's not just the stuff, it's the way that we combine it. It's going to be better later to use, right? And that's what all these normal forms are about. They feel a little theoretical and mathematical because they are, but they have very real practical implications. That when we design our databases better, then we avoid anomalies and just weird ugliness that would happen if our database isn't designed well. All right, so let me take you through 3 of these modification anomalies. First is the deletion anomaly. And the idea here is if you have a table that's not normalized, it's not structured well, and you delete a line, then you may, well, let's look at this. You may end up taking out data that isn't represented elsewhere in the database, and you've lost all record of something important. So for example, if we, in this faculty table, if we delete that row with faculty ID at 389, because we're not offering ENG 206 anymore, but that's the only row that holds information for Dr. Giddens, then we now have no information about his name or his ID or when he was hired. Does that make sense? And the solution is, right, we shouldn't be storing the faculty information in the same table as the course information. They should be separated. So you can delete a row and not lose all record of Dr. Gibbons' existence and employment at the university. Yes. That may be the only class he teaches this semester, but maybe he teaches. Good question. Way to be observant. Appreciate it. Somebody's on the. It's the Sour Patch Kids, isn't it? Okay. On the other end, there are insertion anomalies, which are bad things that happen when you add a new row. This may often take the form of the structure of the table forces us to enter facts about two entities when we just want to enter facts about one. So let's say we've hired this new guy, Dr. Newsom, and we want to add his, right, we're adding his record to the database that he is a new employee here, but we haven't given him any courses yet. So what goes in that last column? I mean, nothing can. So we have some weirdnesses there. Yeah. The last thing is an update. And you can see how these things begin to sort of cross over to each other. The update anomaly means that when we have to update multiple rows when we change one fact. So if we have our table structured like this, we have employee skills, and one employee may have a lot of different skills, but we're also storing the employee's address in each row. So you see employee 519 is good at public speaking and carpentry, and we updated his address to be, say, 96 Walnut Avenue instead of 94 Chestnut Street. But because of the way we have this table structured poorly, in order to update his address, we have to update it in a bunch of different places. That's bad. Follow me? We don't want to do that. Anytime we have data duplicated, then we're going to get weird anomalies like this. All right, so what normal forms do is they allow us to design the database in a way so that these anomalies can never happen. So if you find yourself in a place where you're writing a bunch of queries to do additional information after you do an update or do an insert, do a delete, they're having to clean up a bunch of work, they have to add more rows, check a bunch of rows, and update other values, then it may be because the database isn't normalized like it should be. Okay, the author has this nice table to explain what the different forms solve and the principles that we follow to implement each normal form. So the first source of anomalies are functional dependencies, which we've been talking about. The normal forms 1, 2, 3, and BCNF, which we'll talk about more in just a bit, are normal forms that address functional dependencies and remove functional dependencies from the database design. The principle here is that we're going to design the tables so that determinants are candidate keys. We're going to make the determinants the candidate keys. All right. Each one of those build on each other. So if you have a 3NF table, it's also N2NF and 1NF. It builds on, they each build on each other. Fourth normal form addresses a different problem, which is multivalued dependencies, which we'll talk about later. And essentially all it does is move each multivalued dependency to its own table. So by going through the principles that we're about to look at and increasing the normal form from 1 to 2 to 3 to BCNF to maybe 4, we're eliminating these sources of anomalies so they can't happen. So our database is better and you can process it easier. The last one, there are higher forms. There's 5 and this DKNF, but we're not going to talk about them very much because they really do address some strange oddities and some data constraints. And I really want us to understand the 1 through 3 and 4. All right, so let's build this up. What is first normal form? First normal form just means that the table qualifies as a relation that is according to this list of characteristics that we looked at on the first or second slide. Right? So if a table meets these criteria, then it's in 1NF. Yeah? All right, so let's take it up. To be in second normal form, you have to be in first normal form and meet this criteria. The main idea here is that we're going to remove duplicative data. So we're going to remove subsets of data that apply to multiple rows of a table and put them in separate tables. The data that's in multiple rows, we're going to move them out and put them in separate tables. We'll then create relationships between the new tables and the original tables by using foreign keys to map those together. So we're getting rid of the redundant data. And the formal way of saying this is that all non-key attributes are dependent on all of the primary keys in all of the tables. So it's all about the primary keys, and the non-key, that's attributes that aren't the key, are dependent on the primary key. All right, let's take it up another notch. In third normal form, we go one step further. We're meeting all the requirements of second normal form, but we're also removing columns that are not dependent on the primary key. So there are no determinants except the primary key. Primary key is the 1 determinant. In third normal form, we meet the requirements of second normal form, and there are no determinants except the primary key in each table. And generally, we're going to solve these problems the same way, which is coming up, but it's separating out the data into a different table and then creating foreign keys. So it's the same way to solve it, but we're kind of progressively and more aggressively applying that process. Okay, the last one is this BCNF, that stands for Boyce-Codd, the two guys that defined it. And in this highest level criteria, the highest on this slide, some people would call this like 3.5 normal form, or would see it that way. We meet all the requirements of third normal form, and every determinant must be a candidate key. A lot of these too, as we get progressively higher, I feel like they only solve some really edge cases. You know what I mean? And if you can get something, just like the biggest payoff, I feel like practically, is going from 1 to 2. And then there's less payoff from going from 2 to 3. And then there's even less payoff for being super strict and going from 3 to BCNF. I think so, but I think there must be some weird cases where you could say you meet 3, but you're not BCNF, and therefore you could have some. All right, so here is the process of normalization. So this is what we do to meet those rules, those principles. And it's all about functional dependencies and candidate keys. So we need to understand what functional dependencies exist, what the possible candidate keys are, and then making more tables so that all those things are they're separated out. So we're going to find every functional dependency that exists in our data. Then we're going to find every candidate key. Now we have our while loop. Is there a functional dependency with a determinant that's not a candidate key? If there is, that means we need to break this thing down. So we should move columns of the functional dependency to a new table and make the determinant of the functional dependency the primary key of that table. And then in the original table, we'll save a copy or leave a copy of the determinant. This is basically creating the foreign key in the original table to this new table. And then we would also want to add the referential integrity constraint to make sure that we can't put illegal values in the foreign key table. So this is a fancy way of saying we're just going to create tables with relationships for any functional dependency with a determinant that's not a candidate key. And then we'll keep going through this loop until we have eliminated all of the functional dependencies with determinants that are not candidate keys. And when the answer to that question is no, then we're done. So the point of all this is to eliminate modification anomalies by removing the functional dependencies in relations. So that the functional dependencies, there's only going to be a functional dependency between the primary key and the rest of the data, the other columns. All right, the last thing, which is, this is the additional criteria that is the distinction between BCNF and fourth normal form, is this other problem called a multi-valued dependency. If you look at this little table, employee degree, you see different people's names and the degrees that they hold. And since we know about how degrees work, we understand that there's a very limited set of possible options that can go in employee degrees, right? A multi-valued dependency is when a determinant is matched with a particular set of values. So there's a set of values that are the only legal values. So they denote that like this with two arrows, employee name, multi-determines degree. And another example they have here is if you have siblings, and they would say that the employee name multi-determines sibling. So let's sum this up. We learned all about normalization. We saw how we can take a relation and move it into BCNF by progressively enhancing it through 2NF, 3NF, BCNF, creating more tables. We learned about functional dependencies, how one column determines another column, and that's going to be the things that we identify and then use to drive our normalization process. We also solved the multi-valued dependency problem and how a determinant can determine a set of values, and we can fix that by moving those to a different table, and that'll give us an even cleaner database, a more normalized database, so then we can take a database to fourth normal form. So the stuff we've talked about today is normalization, and the point of normalization is to allow us to design a database like a boss.